Okay, going good. Okay, we'll start in like 5 minutes. Feel free to say hello in the YouTube or Twitch chat or LinkedIn comments. I know LinkedIn doesn't really have a good chat set up for videos right now, but feel free to say hi. Cool. Okay, that looks good. So, FPGA Zealot, we're going to be doing a Agilex, Altera Agilex 5 kind of live stream today. We're mostly going to be looking at using the, platform visual designer tools to use the IP to hook it up together so we can get get a functional design going. We're going to be looking probably in future videos at actually verifying the settings and the software configuration and get the stream actually going. So this is mostly going to be focusing on integrating existing IP video IP cores with the FPGA AI suite. Bring up. Okay. Hopefully, the video is coming through. The audio is clear. Sounds good to me at the moment, and um, we will start in a minute or two and dig deep into the content. It'll probably be a 45-minute long stream. We're going to be mostly trying to show how to integrate the FPGA AI core and its streaming interface with an existing DisplayPort example. Mostly taking these two Altera examples and trying to merge them together to one functional design. That's what we're going to be focusing on today. Guess I'll post on. Okay, that's set up. Okay, we'll be starting in about a minute, and thank you for joining us. Good. Okay, we can start. So it's 10 o'clock. We'll go ahead and start the stream. Welcome. I'm FPJ Zealot or Andrew Wilson. We'll be looking at the Agilex 5. This is an Altera sponsored stream. We'll be looking at the FPGA AI suite on the Agilex 5 and basically taking the DisplayPort example from the Agilex 5 and the AI JTAG example and trying to merge them together. And mostly today we're going to be focusing on what IP cores in the Quartus IP repository we need to utilize so that the data is prepared correctly for the AI core, and potentially how we bring that data out of the AI core and modify the output of the video. So we're going to be looking at mostly the video IP core and inserting the AI core in a video pipeline. So let's start with some socials. If you want to find me, we are streaming on YouTube, Twitch, and LinkedIn right now. You can find me as FPGA Zealot on YouTube, X, Twitch. Find me as Andrew Wilson on LinkedIn. There's also a Discord in the description if you want to come say hi and ask some more questions in our little community. Some disclaimers: this is a Altera sponsored live stream. I am not directly employed by Altera. I do not offer debug support or development support for their products. I love to answer questions and talk about their products, but I don't offer official support. The content in this channel is created for informational purposes only, and all the opinions expressed on this channel are my own. So today we're once again looking at the Agilex 5 on Altera. I've been enjoying using the Altera 5 so far. The dev board that we've been using, there's been some dev board that's actually kind of at an affordable price to demonstrate the features that you want to test. And today we are mostly looking at 4K DisplayPort, and we're looking at using the DSPs. With the AI core and the several DDR banks. We have hello YouTube chat, and morning to you as well. So for this dev kit, we have DisplayPort that we're using for DisplayPort in and DisplayPort out, both supporting 4K. These are what you would call evaluation IP cores. So I can run them as long as the JTAG is connected to the Quartus programmer. But to officially put this in a product, it would need an additional license. We're also going to be using multiple DDR banks. Well, today we'll be looking at one DDR bank, but I want the final demo to use two DDR banks. But we're going to be looking at bringing the video in. We're not using PCIe in this demo. We're mostly using JTAG to communicate. We're not using the HPS at either. But I definitely want to get more familiar with these different options that the FPGA provides. So we're going to break this down into 3 videos over, I guess, the next 5 weeks or something like that. So today we're going to be looking at the block diagram, how we integrate these cores into like a video pipeline. The next video, we're going to be simulating these various IP cores and verifying that the data that we have the correct configuration to get the data properly configured for the AI core, and how we can use the output of that core. And we're going to kind of do that in a little bit of hardware testing and more simulation testing to get that working. And then video 3, we're going to put it all together, and we're going to have a live video going through the AI core, have a box around the picture, and text using. We're probably going to use the ResNet 50 for classification. I would love to get looking at segmentation or something like that, but I don't think I have time to do the video overlay and debugging of image segmentation. But that would be a good one to try later. Maybe next year, early next year, I can look at doing video segmentation of the AI core. So looking more at what we're going to do today, we're going to look at the video pipeline, what video IP cores need to support the FPGA AI core. Then we're going to look at how we place in the FPGA AI IP, and then we'll look at how we hook that up to the DDR4 EMIF and what we would need for a secondary DDR external memory interface. So we're going to start with the DisplayPort example. So we're going to kind of jump ahead to what the example design is. If you look at the previous video where we went through the DisplayPort example and got it working and modified it a little bit, that's a good place to start. But today we're going to assume that we're going to start at the example, the Axie stream example for Agilex 5 DisplayPort. Start with this. So this is a newly generated design, and we are going to modify the streaming interface for I guess parsing or processing appropriately, pre-processing the video frame data for the AI system. We have a question from YouTube. Will this demo use the SoC? It is using a soft Noel 5 processor to configure the DDR. That's right here as a CPU. I am not using the HPS today. There's a I need to work on BSP generation for the SoC to figure out what's the correct way to integrate the ARM processors in the core. So today we're going to be mostly focused on the fabric portion of the video pipeline, and this mostly operates without the HPS system. Okay, so we want to look at this a little space only. So a few videos ago, we talked about this. We have the RX DisplayPort going into a video frame buffer, and this is being written to a DDR bank, the 3B bank, and then it's being sent to the TX portion for display out. So what we want to do is we want to take this display out, and we want to be able to set up to process for a ResNet 50 classification. So what we're going to do is we're going to explore some of the IP cores that are available. So there's quite a few vision cores provided by they have any. So these are the different cores we're going to be looking at. We're going to be using the broadcaster, we're going to be using the clipper, we're going to be using the color space converter, I think the scaler, and the mixer. There's also a text IP overlay that I'm also probably interested in later as well. But there's a lot of different cores that can help us with a really effective video pipeline. So let's build a functional pipeline real quick, and then we can hook it up. Take a bit of time, so might as well get started. So first we're going to do a broadcaster, and this basically is going to allow us to take one Axie stream and broadcast it to multiple locations. So what we're going to do is we're going to do 3 colors, we're going to do 4 pixels at a time, we're going to do 2 outputs. The first output is going to be the normal output, so we don't need to put FIFO there. The second output is going to be going to the AI core after we do some processing, so we'll go ahead and set that up. We're going to just hook this up to the video frame buffer here. Double click this link. And for 0, we're going to add that to a mixer. So let's do the mixer next. Once again, 3 pixels or 3 colors, 4 pixels. We'll do memory control, number overlays, and finish. What we're going to do here is we're going to take 0, get up to broadcast 0, then this output here, we're going to hook up to the TX, and then let's so basically we kind of create like a little place where we can pipe off, do the AI processing, and then come back and apply it to the video frame. So when we have the input for an AI like ResNet 50, we have a fixed size, we have a fixed scaled size, we have a fixed pixels, and we also have kind of like an expected color plane. So the correct way, I think, to do this is we're going to be looking at 3 different IP cores. We're going to be first looking at the Clipper. So this is going to let us grab specific region of the design. We're going to do memory map so that we can change what size of the picture we're looking at. We're going to memory map that. And we're going to hook that up here. And then after we got our offset set up, so we have the fixed resolution size, then we need to appropriately downscale it. And instead of just, like, this will allow us to do really nice downscaling using the normal functions you normally do for downscaling an image, like we would do in Python. So we're going to add this. We want it to be memory control. Did I set that up? Yeah, memory map control interface. Taylor. Video. So go in. Okay. So we're clipping the window. Now we're going to scale it appropriately down to the size we want. Wonder if we should do the color filtering. No, you usually do the color filtering right before. To mimic kind of what we see in the other interfaces, we then do the color plane space converter here. We're gonna have, okay, so number of pixels. Do a memory mapped interface. Okay, and then we're going to start by identity matrix, hopefully. So this will allow us to do basically a 3x3. If I turn off the memory map, you can see what this is doing. So right here, we have dout 012, which is RGB basically, and you're going to do a coefficient of the other colors plus a bias. So this basically acts as our color space converter, and this is usually necessary for getting the color range to match what the AI core has been trained on. So we'll just go ahead and do it this interface. And then for now, we're just going to return that to here and try to get this design validated. For the control interfaces for these various systems, we're going to go ahead and just add a JTAG to Avalon Master Bridge. And so we could control this over JTAG using our IPy notebook interface. Oh, there's too many lines. Flipper, scalar, scalar. Scalar, color space converter. Got that? Okay, okay. Okay, that's all the ones. We also want to connect this to the DDR address exit. Okay. Next I want to assign the addresses. So for the CPU, I want to lock down all the CPU. I don't want this to change because the software's already been compiled. We're going to lock down everything connected to the processor. Let's go ahead and lock down things connected. Probably have to disconnect that one later. Wanna, yeah, let's get that one going. Okay. Before we do that, I want to go back here. Off that code. Okay. That down. Now here we need to assign those ones. I'm gonna go ahead, auto assign. This connected to those. Okay. So if we try to validate this, it's going to talk about how the clocks. If you have a question that's not related to the presentation, feel free to go to our Discord. So there's a Discord link in the description. If you go to the Discord, you can ask questions and we can talk about it there. It's a good place to talk about other FPGA questions later. Okay, so we have got the interfaces all set up. Now we just need to get the clocks, and then we can validate and generate, and then I can talk about the AI core. Okay, so this should not take too long. We're just going to connect these all to the Agilex bus system. All on the same clock. Uh, clock on we gotta get the J tag. Down with the J tag. I like how it lines everywhere, but it is not hooked up to it at all. Okay. Okay, so we should be good to validate now. Okay, we have a validated system. We're gonna generate it, we're gonna save, and I'm gonna show you how to generate the AI, the API, the FPGA AI IP. Okay, so let's generate this. Okay, now we can close this. We're gonna go ahead and hit compile design while we go back and talk about how we're gonna connect the AI core. So, if you're joining us right now, we just went through kind of a video pipeline to take I guess a portion of a video frame, scale it down, do color plane change, and then potentially like overlay that back onto the image using a mixer. And then we got be happy and compile. Now we're going to insert the FPGA AI core
in that pipeline. So it's going to use the pre-processed data and hopefully set up an output. This is an Agilex Altera live stream. I am FPGA Zealot, and this is sponsored by Altera. So thank you for joining us. If you have any questions or comments, or your YouTube chat, Twitch chat, LinkedIn comments, I should be able to see them all pop up and be able to respond to them. Today is mostly going to be about interfacing existing IP and setting it up correctly so the tools are happy and willing to compile. And then we're going to be looking at software configuration in the next video and doing a full integration in a video after that. So next, we're going to be looking at the FPGA AI IP insertion. So first we got to create the AI core. So I created a architecture here, kind of a basic architecture. But the important things are we are targeting our FPGA, the Agilex 5. We are not using the parameter ROMs. We're going to be pulling the ResNet 50 out of DDR. We're going to use a lightweight transformer for the streaming input interface, which is going to be 96 U8. Then we have our input and stream. The output stream, I just set to 32 bits. I'll have to figure out how that works with the ResNet using some side hardware testing. And then we have our kind of various other interfacing crossbars that match what you would see in architecture. So like last stream, we're going to go set up in the following the core DLA kind of workflow, we're going to make a new directory to generate this IP core. Here, background, see the number. Okay, so we're gonna go to core and go DLA IP dash. Right. So we're gonna first do IP directory. We're just gonna make it right here. Depot flow. We're just going to create key. Then I think we just need to point to the arch. So we just gotta go arch, be up in the other folder. So this is how we create our IP core. It's relatively easy. It's not complicated at all. And then what we're going to go here is we're going to go to our IP and development. And we're going to add a project specific core here. Do C, grab it. We'll choose add, apply. On the right, we have an FPGA AI suite up here at the top of the IP core, right here. So for the pre and processing, so okay, we can go and insert the core. See, should be able to pop it up real quick. So we're going to insert the AI core, and we're going to show you some of the issues you have to deal with. So we would want to insert the AI core right here. So let's go back to interface only view so it's simplified. Okay, so we have a question from YouTube about the Arch file. So the Arch file is like upper level description of the AI core configuration. So this is like normally you would see this in GUI and you pick all the different options. Right now they're trying to figure out a good GUI option. So right now we're using kind of an XML, not an XML file, but like a just a simple text file to explain what the AI core will be using and doing. Another question from YouTube asking about ultra scale. We'll be exploring other vendors in videos later in December, but I hope we'll be able to explore both the Altera and the other vendors later. So we're going to add the FPGA AI suite core. We're going to pick the streaming, and we're just going to do default interfaces over here. So if we look at the output of the two streams here, right? So this is a color space converter. It has a valid, a ready, a last, a data, and a user. Our AI core only has a valid, ready, and T data. So we need a way to figure out if we need a way to pre-process this data um, to remove the T last and the user. Maybe we can ignore it. Maybe we can just do like like little direct connections, which don't seem supported at the moment. But to do that, we're going to add a module, and this is basically going to be our AI pre-buffer station. So I have some files set up. They're just they're similar to what we did in the DisplayPort stream of creating interfaces and modules for the system. Probably popped some. So what we're going to do is we're going to delete this connection, and this is where we're going to insert the AI. So we're going to take the color space, hook it up to our pre-processing, then we'll take the pre-processing and we're going to hook it up to the AI stream. And we're going to hook this one up to our JTAG Avalon master. Well, and right now this is mostly just a black box. I will have to go in and define the implementation better, but this is just so that we have HDL that is agreeing with this interface and HDL that is agreeing with this interface over here. So we have a kind of preprocessor HDL node. YouTube, we're asking for documentation for this. I will provide documentation going forward in December about this as I get it actually, working with the correct configuration. There's still a few things that need to be refined before I can post a correct configuration. So I have to do some more testing and get the configuration correct, and then let's see, in future streams I'll have the documentation available and we can walk through it. We're gonna hook this up to the JTAG master as well. This output stream. So let's look at the output stream. Looking at the output stream, this output stream has valid, ready, last data of 32 bits and a strobe. This does not line up with the expected 96 bits of video and whatnot data. That's because the ResNet 50 is sending out a list of 1,000 things and providing confidence for it and not providing image data. So to do an overlay, you need to add a post-processor, a post-processing buffer to the system as well. So we're going to go here, post, call it the AI post of it. Now this has popped over. So we're going to hook this up here, this one up, this guy. Now we should be able to right click and hit refresh. Here's our video pipeline. So this video pipeline, we have the raw image that is going right here and is going to the mixer. Then we have clipper, scaler, color space converter, a pre-buffer into the AI suite, and then out of the AI into a post buffer, which will create the overlay, and the various interface to hook it up to the AI core. And to get this compiling, we're just going to hook this up to the DDR expander. Here's the node. This up window for the DDR. Work. I'll leave the interrupts disconnected. So we're going to now jump into the default view to hook up all the clocks for these systems. And they're just mostly going to be the same Axies. AI. So I think the DLA clock will keep on the Axies domain. Might want to put in the DDR domain. Keep that Axies DLA reset. Let's go ahead and put that on the JTAG master reset. Awkward. Okay. Yeah, that's what breaks. Actually, put you Axies. DDR clock. We're just going to hook to the DDR system. Interrupt clock. Down the Axies. Okay, so we should be good there. Now we need to assign addresses. So for the JTAG, we've added these systems right here. So we're just going to auto assign those addresses. And now the JTAG master can communicate with all these various interfaces on the video pipeline. And we'll validate it. We missed a clock in the post buffer. So we have a question from YouTube. Does the FPGA AI suite contain ResNet 50 information? It is a generic AI processor. So it can do ResNet 50. It can do other things. I'm going to specifically target ResNet 50, but it's using the Intel DLA compiler to be able to handle various different interfaces. Hopefully, the setups would allow us to take any type of frame data, resize it, and recolor it for the appropriate thing. It's going to be the post buffer, maybe a little hard. Maybe we need to throw in a soft processor there for the post buffer and overlay so that we can do a more generic system for that. But that's something to think about. Validate. Okay, that's what we expect. We're going to go ahead and save and generate. I know this is building in the background, but we'll probably have to stop it. We're going to clear the previous, multiprocessor, create system Verilog top level, hit OK. Okay, now close this. We made it this far. We're going to go ahead and stop it. So our design made it through the fitter stage. Let's go ahead and look at the place utilization summary. So without the AI core, so this is without the AI core, we're using 20% logic, 24 or logic utilization, right, ALM utilization, DSP blocks, memory, or MSP blocks. Okay, so memory, DSPs, and the logic elements. Now we're going to recompile this with the AI core. So we have a great question from YouTube about how many networks can be utilized. It's mostly what fits on the FPGA, right? So we have this architecture file. This architecture file talks about what resources the FPGA is using to implement the core. There are some there are some type of layers. If the layer is static and already like pre-supported for the FPGA, it can be relatively easy to do your own network. But if you're using like the more advanced YOLO that has some, I don't know, dynamic layer setups, you may need to go into the network and instead of having like dynamic sizes, do static sizes so it works better within the FPGA architecture. So you can run YOLO, but you might need to go in for the advanced models and constrain it in some ways, which can be daunting when you're pulling up like an Onyx file and trying to figure out how you can constrain the model to handle um, static sizes rather than dynamic sizes. Another question. So yeah, I've used YOLO V2 and I played around with YOLO V8. I think it's a lot more difficult to get the other ones set up, but it'd be great if we can get some examples set up for more of the, I would say, state of the art models. Another question is the AI IP core used soft in fabric or hardened core built into the FPGA? So one of the it's a soft core, but one of the cool things about the Agilex 5 and the Agilex 3 FPGAs is that they added convolutions to the DSPs. So instead of having like a hardened AI core in the FPGA, what they've done is they distributed AI functionality into the DSPs. So when you create an AI core, it's going to use this new advanced tensor function in the DSPs to be able to kind of accelerate that functionality within the FPGA. So you can use the distributed DSPs to implement the core, which is a different approach than other vendors. So right now we are compiling with the AI core. We can look at the utilization after that. But I want to talk about the DDR interface. We're going to be looking at adding an additional DDR bank. I need to probably dig more into that and probably have more information later, but we can go through the beginning steps. If you're joining us now, about 40 minutes into the live stream, we'll scroll up to kind of the intro slide. I'm FPGA Zealots. We're doing an Altera sponsored stream on the Agilex 5. We're trying to integrate DisplayPort example and the AI example together into one design, and trying to see how the robust IP repository allows us to do that without generating custom HDL for every single stage. And so we've got the video pipeline going. We are clipping the image, we're scaling the image, we're doing the color space conversion. We've inserted the FPGA AI IP core that supports streaming input and streaming output and reading the model out of a DDR bank. Right now it's sharing the same DDR bank as the frame buffer, and on this FPGA we have multiple DDR banks, so we should try to use a different DDR bank for the AI core. Okay. While this building, we going to jump back into the visual system so that we can talk about the external memory controller. Okay, we have a YouTube question about running YOLO V2 tiny model with the DLA benchmark. You're talking, I'm not exactly sure what a deserialization, not deserialized by device XML means. It sounds like maybe the XML that was loaded onto the HPS was not correct, not matching the model. I haven't played around with the YOLO V3 tiny model. I had to kind of look around for some specific models that that work better with the heterogeneous AI implementation. But feel free to post information in in the FPGA Zealot Discord, and we can figure out more information later. I don't have anything at the moment. I think. Okay, so we want to do another EMIF controller so that we can support the other bank. Best way to. So we'll try to walk through this the way where you expect to do this and kind of show where it gets a little bit we'll say confusing. So the default implementation for this is matches up with what's kind of done in the other system. Let's go ahead and pull up the other system. Okay, so how much resolution will it support? Uh, so the DisplayPort example is doing 4K at 60 frames per second, which is pretty good. I do think you could go faster if you wanted, or more data rate, but 4K 60 frames is a pretty good benchmark at the moment. Go ahead. Look at what the JTAG or the DDR interface we want to hook up to. So yeah, 4K resolution. The play port. Okay. Okay. I want to. So I'm pulling up the parameters for the DDR that the JTAG example is using, which is a different bank. We can look at both and try to update it to match as we expect. So go. So we're going to be doing operating frequency of 800. We're going to reference clock to off the sideband. We're going to turn this to 5. And then we have this pin mapping, which is very important, that defines the I/O. I'm probably gonna do a video about DDR interfaces in general and the Agilex, so we can figure a little bit more about that. Then we have a few advanced timing parameters that we want to set up. So we're gonna do read latency. We're gonna do a write latency. We're gonna add 1, 2, 3, 4. We're gonna do here. We're gonna do a TR. Ah, now we're just going to line this up with what we have on the rights. 12, 11, 50, 90, 5, 5. Okay, so that's set up. The analog options. Defaults. Defaults. Now when we finish this, we're going to go back to our visual designer. Now we have another memory controller. For this, these interfaces, the clock right here, export that, the mem interface, export that, Axie lights. We're going to connect to this calibration device right now. I need to figure out how to get multiple calibration. This was not in the IP repository. To figure out what's the best way to add that. We'll set that up. And we want to do another I/O expander here. Not a good way to duplicate them, but we can. I guess we're just going to add the 4 span extender. Data path width is 6. 36, 33. Turn off the control. There. Right. That's false. Okay, burst count. Let's do 7. Slave. Well, that should be 32. And we want 32 bits. 7. Okay. Slave address span cannot equal or exceed the master address. Okay, then what are they doing in the other system? So let's go back here. Flip. Here. Where's doing? Okay. 4 gigs. Okay. Word versus byte addressing. Okay, I'll take that. This is data pair. Oh, it's a data path width. Okay, that's what's. Okay, so back here. So, sorry, went off on a little journey. Yep, that's what we want. This guy, we're going to turn off the AI core for that one. We're going to hook up the AI core to this one. Okay. Now we gotta go do the clocks. So we haven't set up the clocks on that one. But we want the Axiolite one to match. So these are going to be the MMC. The MMC are the management clock here. The figure out what that is happening. This one's the, where is our other? Here. Where's this reset? This reset is Ethernet reset bridge. Clock out is going there. So we're just using the clock out default. Okay. So these need to go. These ones are a little. Alright, we should be done with this soon. Clock out. It's going to go to. Yeah. Reset. Probably the EMF reset later. Okay. What happened with those on control ready? Okay, they're using the control ready as a reset line. Okay. Mem reset is being exported out. let's go do that real quick, and then we're almost done. Figure out how. Okay, and that's going to. So this one go here. And the only thing to change is the AI core. The DDR clock needs to change to the other one. And then we're done. Okay. We also will have to set. Oh, okay. And then refresh everything. Up. Okay. And then I gotta go to addresses. We gotta auto assign addresses. Validate the system. Ooh. Sorry it took so long. Okay, so we have a question on YouTube about the use of external RAM. Sorry, I got distracted for a few minutes trying to set up. So, yeah, you have the option to put your model for the AI core in the Arch file. You have the option to put the model inside internal RAM or in the external DDR. So we just put the external DDR bank here, and the idea is that the model can be very big. So we're going to have a dedicated, right now, 4 gigs dedicated 4 gigs in external DDR bank for the model. So we can do more complex models than what we could do out of the internal memory. So this will allow us to do YOLO and other larger models that wouldn't be available if we just use the built-in FPGA memory. Okay, before we generate this, let's go back here. So we're still here, but we can look at the placement. So we jumped from 20 to 40 here. What the MK? Oh, that jumped from about like 20, 80. So we're using a lot more of those memories in AI core, and the DSPs increased about 2. Um, where's the DSP information about AI function? Okay. So we can go ahead and stop the fitter here, and we're going to regenerate the core. And it's going to be unhappy because the IOs are not existing currently. So here, though, we can go ahead and generate. Okay, yeah, so good question. We had a question on YouTube about what is in the pre and post buffer. I'll just go, if you look at the DisplayPort video earlier, I do go into more how that works, but we can go look at the VHDL for it. You can do VHDL or Verilog. So okay. Just set up. Okay. Here. We'll generate the core. So the pre-buffer and the post-buffer, right now they're just kind of placeholders. We have the Axie light interfaces, and then we have Axie stream in or out and Axie stream in. And the logic right now is just a very basic placeholder. These are just kind of doing colors. I'm gonna have to do the pre one is probably gonna be statistics, just looking at the data, make sure the data is flowing correctly. And then the output, we're going to need to do an overlay with determining what is the confidence, like what is the most confident output of the ResNet 50, and provide that as a text overlay for the DisplayPort stream. But right now they're just placeholders where I have the interfaces set up correctly, and once we get everything going, we can then modify these files with the appropriate pre and post processing that we want in our video pipeline. So the only issue we have now is we need to bring cores to the top. So I guess we'll just copy this quick. FB this this port is called that. Okay, so to look at the instantiation file, I think we're going to poke around here to our stream example. Stream Cordis to source system, GP core, top level. Oh, it's just all these mems. Want back here. Reset. Okay. Sharing the same cow done, so we don't need to do. Then ref clock at where's the that? What's the see if I can find where that. Oh, I guess we'll try synthesizing it, see what happens. So we're gonna do E there, down here, E here, these. Okay, so we'll see how well the synthesis. Okay, we can do some questions while we're compiling, but we're probably close to finishing the stream. It's 11 o'clock. So that was kind of the process of going from the DisplayPort example, increasing the video pipeline to do a kind of a parallel stream for data processing, adding the AI core, adding dedicated DDR for the AI core. Okay, good. We got the error. I want to see which signal I'm missing. Here's the okay, that's DBIN. Okay. Yeah. They called. Oh yeah, we're not doing ECC, so that's why we don't. here to the top left. Only supposed to be 2, 31. Where is D? So the original one had ECC. We're not doing ECC on our interface. We're going to just be doing raw data. We can look at probably implementing ECC properly, and that way we can have that correction, but we're not going. Okay. Well, thank you for all your questions. I know this was more of a slow live stream, just going through all the different cores. And you find a way where we can. I probably should try to release the simulation files next week so people can open them up and look through them as best as possible. Maybe like do a little report so you can walk through. We can walk through them quickly. So we have a question about the Neos 5 in the design. So the Neos 5 in the design is handling the DisplayPort. It's doing all the DisplayPort training, lane training, and setting up the resolution correctly. We're gonna probably add another Neos 5 to handle the taking the ResNet 50 output, so a list of 1,000 items, determining which one has the best confidence, looking it up from a table. So like item 777 is a plate, and then loading that plate into a text overlay. We might want to put like a Neos 5 processor on the output of the AI core to translate the output of a layer of the network into something that's useful in the overlay. So I would love to be able to handle different networks and be able to use the same core, but we're going to have to see what type of overlay we're going to need to line up for all that. Okay, once the synthesis finishes, we can maybe look at the pin planning, and then we'll probably call that it. But okay, so in 2 weeks, we'll look at doing simulation of some of these video IP cores to see how the video frame is parsed and processed. Then we'll be looking at 2 weeks after that at a full operational of a network with DisplayPort data flowing through the FPGA. There's a lot more work to this example than we can go over into a single video. We'll take the last few minutes of questions, look at the pin planning, maybe a utilization, but that's probably it for today. Feel free to leave a like. I hope this content is useful to someone who wants to do a video pipeline on the Agilex 5, and hopefully we can integrate real-time edge AI to be able to do that in some more video applications, whether that's, I don't know, for a car or for a smart camera or something like that. Okay. I want to look at the synthesis report. Okay, it's almost done. So look at synthesis report, we'll look at pin planning, and then we can finish up with any questions that are in the chat. So if you got any questions in the chat, put them in now. We'll respond to it over the next probably 5 minutes. Then we'll probably have to finish the stream for today. So the goal is, so we have a great question from YouTube. If I want to use other networks every time, we need to generate FPGA AI suite IP, integration, compilation, deployment. So the goal is that we can abstract away the network deployment and the FPGA AI core, so that we can hook up, we can dynamically hook up data, send whatever data we want to the AI core, and be able to use different networks.
So the goal is that we're going to load different networks into the DDR dedicated to the AI core, and that all those networks would take in a video frame or a video image of so many of any resolution. We can handle any resolution using our video pipeline clipper, scaler, color plane converter, color space converter, so we can get it working for any AI core. And then in that post buffer, we'll probably have to add a NEOS 5 processor to do kind of smart processing of the output of the AI core, and then add it to an overlay. So there's going to be kind of hopefully in the end we'll have one FPGA image. We'll be able to load in different models, and then we'll have different software loadouts for the NEOS 5 post processing, so that we can add the appropriate overlay to the image. That would probably be the goal. Okay, so synthesis report. Resource use. Uh, and okay, that's just the JTAG stuff. So this I look at hard to get the map to the FPGA yet. Okay, so here's the resource utilization. Doesn't really have the DSPs. Right here, DSP summary. Floating point, register, then the resource utilization, DSPs, memory, informational. Okay, let's first here, I guess it's okay. So now we can go to pin planner, and we now have additional pins by name. So we need to assign all these pins here, up here. This is our new memory bank, and we need to go in and assign all these pins, and hopefully that memory bank works. I'll need to add another calibration core to get it fully working. So I got 4 weeks to get this up and running, so everyone can have a good thing. We might be delayed. We might need to decrease the amount of videos. We'll see how it goes. I might do additional videos during the week to kind of talk about the complexity of these cores. But yeah, do expect more documentation. Do expect an article that walks through these different subsystems and explains, I guess, how you go about designing something like this. Hopefully we can explore more video pipelines. It'd be great if we could just explore each of these different IP cores and how they work, but that would be more time than I currently have. But it'd be great video series or article series. So thank you for joining us. Feel free to like the video, subscribe, repost, whatever you feel is necessary. Do join the Discord if you want to talk more. We can talk more about FPGAs and any different situations you have seen with what you're trying to implement. But thank you for joining us. Thank you for Altera for sponsoring this video. I will see you